All right, let's get into the kinetics of equilibrium. So we're just going to look at a simple first order equilibrium expression, but it will create the basis for how we can think of more complicated equilibrium expression. So imagine we've got the simple equilibrium between A and B. And let's suppose that that is a first order reaction, both in the forward and reverse. So something that we want to start getting used to in kinetics when we see equilibrium is separating this into two reactions. One, A goes to B, and that happens at rate constant K forward, and the other, B going to A, and that happens at rate constant K reverse. And it's important to know that these don't necessarily have to occur at the same rate, and in fact, rarely are occurring at the same rate in most equilibria expression. So from that, we could start writing individual rate laws, right? I could write that the rate law for A was negative dA by dt, and that would be K forward times A. And then I could also write the rate of B, that would be, and the way that I've got it written, negative dB by dt equals K reverse times B. But now what we need to do is combine these two expressions because we recognize these reactions will be occurring simultaneously. And so remembering that negative dA by dt equals positive dB by dt, then we end up with the following. So we can say then that dA by dt equals negative K forward times A. But then similarly, dA by dt will end up equaling positive K reverse times B. So these things will occur simultaneously. Both rates will happen at the same time, so we have to combine those. And when we combine those, we get the following. dA by dt equals negative K forward times the concentration of A plus K reverse times the concentration of B. And now to do anything in terms of this equation with the calculus, we've got to get both dependent on either dA by dt or dB by dt, right? So it's something similar to what we did in the second order reaction that was first order in A and first order in B. So typically in an equilibrium reaction, the initial B concentration will be 0, not always, but typically. And additionally, we could say that the concentration of B at any time in the reaction, I'm going to put a T there to know that that's at any time in the reaction, will equal the initial A concentration minus A at any time in the reaction, right? So, and again, because this is a one-to-one reaction in this equilibrium, so any amount of A that reacts, that's going to be how much B that's formed, right? And we can see that in the kinetic profiles. So now in this total rate law, we can write the following. We can say dA by dt equals negative K forward times A plus K reverse. And we note here that B, that really does mean B at any time t. So now that's just going to be equal to A0 minus A, and I'll drop the t because we recognize that that is A at any time. And then now we've got an expression that we can solve. And so just collecting like terms, we end up with the following. dA by dt equals negative, and I'll write that as K reverse plus K forward times A plus K reverse times A initial. So this is another diffie Q, so that is differential equation, and this is not straightforward to solve that thing. So I'm gonna put the solution to that down on the next page here. So again, just recognizing that we ended up with the following: dA by dt equals negative k forward plus k reverse times A plus k reverse times A initial. So solving this thing for the concentration of A at any time, so right, separating the appropriate dependencies and integrating both sides, we end up with the following. So k reverse plus k forward times e raised to the power negative k reverse plus k forward, all times t. So all of that is in the exponential of raised to the exponential, right? And then that's all divided by k reverse plus k forward. And all of this is multiplied by the initial A concentration. Okay. So what we can also get from this is an expression for A at equilibrium. So if we note here now in this reaction, if I let this, if I increase this K, we can see, where the equilibrium concentrations are being achieved, right? And no matter how much I increase or decrease K by, those equilibrium concentrations are the same. It's just the amount of time it takes to get to them changes based on whatever the value of the rate constant is, right? So what that means is we can achieve equilibrium if we allow T to tend to infinity. So if we say T approaches infinity, we will eventually get our equilibrium concentrations. And so when we do that, when we plug in infinity into here, e to the negative infinity is a very, very small number, small enough that we can effectively ignore it. And so now that means my A at equilibrium equals the following. So that's going to be k reverse. That whole exponential term drops out. So it's just k reverse divided by k reverse plus k forward, all times the initial A concentration. So that's pretty cool. And then similarly, that would allow us to compute an equilibrium concentration for B if we so desired. And additionally, we can also get an equilibrium constant out of this thing when we recognize that at equilibrium, the forward rate will be equal to the reverse rate. So in other words, at equilibrium, K reverse times A, sorry about that. I was thinking A and then writing B at the same time. So and I wrote it all wrong. Let's start over. Okay. So the forward, let's just write it like this. Forward rate must equal reverse rate at equilibrium. So what that means is K forward times A must equal K reverse times B. And if we do a little bit of algebraic rearrangement, we end up with the following. K forward all divided by K reversed. So I divided K reverse over to this side, and then now we have to divide B over to the other side. Okay, so K forward over K reverse equals B over A, which equals the equilibrium constant. So, and it's also really important to note that this is only an approximate result because, again, Ks are not dependent on concentrations. They're dependent on activities, right? So this is only approximate, but works to a pretty good approximation. And if we have multiple equilibrium steps, so in the same way that we would multiply all those rate constants together in a complex mechanism, we could do the same thing with their rate constants. So now what about a Le Chatelier's principle? Okay, so we call this relaxation methods. So suppose we're monitoring the concentration of A and it's achieved equilibrium. And we've imposed some type of change. So impose a change. And that could be a change in temperature, it could be a change in concentration, it could be a change in volume, and so forth. Well, we would see this response, and then we would get a new equilibrium. So for example, let's suppose we're monitoring our concentration versus time for this simple first order equilibrium reaction, and we're looking at the ratio of A initial over A. So we know that A will decay exponentially, and certainly if we were monitoring B, we would know that B would grow exponentially, okay? So, and actually, to make that clearer, we should note that this concentration scale is generic. So I'll write J, noting that that could be the ratio of concentrations of A or the ratio of concentrations of B. And actually, I hate the way I drew this, so let's start again. Let's make this look nicer. Okay. So we've got this exponential decay in A, and we've got exponential growth in B. And now they achieve some type of equilibrium. Okay. So if we impose some change that preserves the ratio of the equilibrium constants, right? When A shifts, so let's suppose A shifts down in some way, right? Because we've imposed some type of change, B will have to have the same corresponding shift, right? Or suppose we enact a change that causes the concentration of A to increase. Well, then we know the concentration of B would have to decrease. So we would see a series of these, what we call relaxations or responses to equilibria. And it's important to note that that amount of A over B, as always, will represent our equilibrium constants. And if those changes resulted in a change of equilibrium constant, right, from changing the temperature, then we'll see a new ratio. If it was just like a simple like add more A, then more B is produced, and we will have preserved those concentration ratios and thus equilibrium constants. Okay, so that is all that I will say about equilibrium for now. I'll see you in the next video.